There's a story we tell ourselves every time we look up, that the moon has always been there, steady, silent, unchanging, a permanent fixture in the sky as natural and inevitable as sunrise, as old as Earth itself, as permanent as anything in the universe can be. We've built calendars around it, written poems about it, navigated oceans by it. It feels, in some deep and unquestioned way, like it belongs there, like it was always going to be there, like the sky without it would be incomplete. That feeling is wrong, and not just slightly wrong. The moon may be the most violent secret in our solar system. For most of human history, and even through the early decades of modern science, the question of where the moon came from didn't seem particularly urgent. It was just there. Some astronomers proposed it had formed alongside Earth, born from the same cloud of gas and dust that gave rise to our planet. Others suggested it had formed somewhere else entirely and been gravitationally captured as it drifted too close. Both ideas had a quiet, orderly logic to them, the universe producing companions, the way nature produces pairs, gently and inevitably. Neither of those ideas survived the evidence, because when scientists actually started doing the math, measuring the moon's mass, its orbit, its chemistry, its relationship to Earth's rotation, the gentle stories began to fall apart. The captured moon idea failed almost immediately. The geometry doesn't work. The odds of capturing an object this large into a stable, nearly circular orbit are effectively zero without something dramatically slowing it down. And there's no convincing mechanism for that. The co-formation idea failed too, but more slowly and more painfully. If the moon formed from the same disk of material as Earth, it should look chemically like Earth's outer layers, and it mostly does. But there's one glaring problem. The moon has almost no iron core. Earth has a massive one. If they grew up together, why is one of them so iron poor? The simple story keeps breaking against the details. And then, in 1975, two planetary scientists named William Hartmann and Donald Davis proposed something that, at the time, sounded almost too violent to be taken seriously. They suggested that roughly 5 billion years ago, when Earth was still young and partially molten, something hit it. Not a small rock, not a stray asteroid. A body roughly the size of Mars, an entire protoplanet, which researchers have since given the name Theia, plowed into the early Earth at a tremendous angle and at speeds measured in kilometers per second. The collision was not an impact in the way we typically imagine impacts. It was more like two partially molten worlds merging and tearing simultaneously. Theia's iron core sank into Earth's interior. The outer mantles of both objects were violently ejected into space in a spray of vaporized rock, superheated gas, and debris. That ejected material, still bound to Earth by gravity, eventually coalesced in orbit. It clumped. It cooled. It became the moon. This is called the giant impact hypothesis. And the reason it has dominated planetary science for decades is not because it was a bold idea, but because the evidence quietly, relentlessly lined up behind it. Start with the moon's composition. Lunar rocks brought back by the Apollo missions, 12 actual human beings who walked on that surface between 1969 and 1972, showed that the moon's outer layers are dominated by silicate minerals very similar to Earth's mantle. The moon is, in a meaningful sense, made of Earth stuff. That makes perfect sense if it was torn from Earth's mantle in a catastrophic collision. It makes almost no sense if the moon formed independently somewhere else. Then there's the iron problem. Theia's iron core, according to the hypothesis, merged with Earth's core during the impact. What ended up in orbit was mostly mantle material, rocky, silicate-rich, and iron-poor. The moon's core makes up only about 2% of its mass. Earth's core makes up about 30%. That asymmetry is one of the strongest fingerprints of an impact origin. Then there's angular momentum. The Earth-Moon system spins with more rotational energy than you'd expect from a planet that just formed quietly in a disk. Something gave the system an extra kick. A giant oblique impact, of the kind Hartmann and Davis described, would do exactly that, imparting a tremendous amount of angular momentum into the combined system, which is still visible today in Earth's spin rate and the moon's orbit. And then there is the lunar magma ocean. When the moon first formed from that spray of debris, scientists believe it was entirely molten, a global ocean of liquid rock thousands of kilometers deep. As it cooled, lighter minerals floated to the top, forming the pale ancient highlands we see on the moon's surface today. Those highlands are dominated by a rock type called anorthosite, which is almost exactly what you'd expect from the slow crystallization of a magma ocean. This feature is not easily explained by any other formation model, but it falls naturally out of the giant impact scenario. For a while, the case felt almost airtight, and then the scientists went deeper and found a puzzle hiding inside the evidence. When geochemists compared the precise isotopic signatures of moon rocks to Earth rocks, essentially the atomic fingerprints of specific elements, they found something unexpected. The moon and Earth are nearly identical at the isotopic level, including for oxygen, titanium, and chromium. This is unusual. Different objects that formed in different parts of the early solar system tend to have measurably different isotopic ratios. Mars has a different signature. Asteroids have different signatures, but the Moon and Earth are almost indistinguishable. The problem is that in the standard version of the giant impact scenario, a large fraction of the Moon should have come from Theia, not from Earth. And Theia, if it formed in a different region of the solar system, should have had a different isotopic fingerprint. So why don't we see that difference? This is where the science becomes genuinely unsettled. And rather than papering over that, it's worth sitting with it, because it's exactly the kind of productive tension that drives discovery. Several explanations have been proposed. Some researchers suggest that Theia happened to form in a region of the solar system with an isotopic composition nearly identical to Earth's. Possible, but it requires a specific kind of luck. Others have proposed a much higher energy version of the impact, one so violent that both bodies were essentially vaporized and completely mixed, erasing any original differences between them. Still others have explored the idea of what they call a synestia, a rapidly spinning, donut-shaped cloud of molten rock created by the impact, inside which the Moon formed in intimate chemical contact with Earth's material, explaining the similarity. And a few researchers have even proposed that the Moon may not have formed in a single impact, but in a series of smaller ones, gradually accumulating material from multiple events. None of these refinements have closed the question entirely. The giant impact hypothesis remains the leading model, supported by more evidence than any alternative, but scientists are still actively debating exactly what kind of impact produced the Moon we see today. The broad story is almost certainly right. The fine print is still being written. And here's where the science stops being just a geological puzzle and becomes something far more personal. Because if the giant impact hypothesis is correct, even in its broad outlines, then almost everything we associate with the Moon's influence on Earth is the downstream consequence of a catastrophe. The tides that pulse through every ocean, every day, twice a day, driven by the Moon's gravitational pull, only exist because a planet died here billions of years ago. The 5-degree tilt of Earth's axis, which gives us our seasons, is stabilized over geological timescales partly by the Moon's gravitational influence. Without the Moon, that tilt might wobble chaotically over millions of years, swinging between extremes that would make Earth's climate unrecognizable. Some researchers have argued that the Moon's stabilizing influence on Earth's spin and axial tilt may have been one of the quiet, background conditions that allowed complex life to develop and persist here. That idea is still debated. The degree to which the Moon is truly essential for life's emergence is not settled science, but the possibility alone is staggering. It means that the violence which created the Moon, the destruction of an entire world, may have been precisely what made this one suitable for us. So here's a question I want you to sit with and answer in the comments below, because I think there's no single right answer. When you look up at the Moon tonight, knowing it may be the debris field of a planetary collision, knowing Earth survived something that should not have been survivable, does the Moon look like a wound to you? Or does it look like a scar that healed into something beautiful? Tell me what you see, because that question touches something deeper than astronomy. The broader scientific picture is both humbling and astonishing at the same time. The standard model of solar system formation, a disk of gas and dust condensing under gravity, giving rise to rocky planets through collisions and mergers over hundreds of millions of years, still describes the broad outline of what happened correctly. But inside that outline, the early solar system was not a slow, patient process. It was a demolition derby. Hundreds of protoplanets colliding, merging, breaking apart. Entire worlds destroyed and absorbed. The planets we see today are not pristine objects that formed smoothly. They are survivors of extraordinary violence, their interiors and surfaces shaped by catastrophes we can only now begin to reconstruct. The Moon is the most visible reminder of that. It sits a mere 384 kilometers away, close enough that you can cover it with your thumb if you extend your arm. And every feature on its surface is, in one way or another, a record of violence. Impact craters, layered over impact craters, ancient mare basins flooded by volcanic rock billions of years ago, a crust born from a magma ocean that itself was born from a collision. The Moon doesn't just record Earth's history, it is Earth's history, broken off and placed in orbit for us to read. What makes this especially powerful is the scale of what we almost lost. The early solar system was unstable enough that the collision that made the Moon could easily have gone differently. A slightly different angle, a slightly different velocity, and the debris might not have coalesced into a stable companion, or the impact might have been so severe that Earth itself was rendered uninhabitable. We are here. This planet is here, with its oceans, its seasons, its life, not because the solar system was gentle, but because a specific kind of catastrophe happened in a specific kind of way, and the wreckage formed something that helped make the chaos survivable. That is not a small thing, And it is not a settled thing. Researchers are still refining simulations of the impact, comparing isotope data with new models, and debating the exact conditions under which the moon assembled. Some questions about the moon's birth will likely remain open for years or decades, but the core of the story, the violence, the evidence, the improbable aftermath, is as well supported as almost anything in planetary science. We live on a planet with a companion that should not exist by any simple reasoning. A companion that is, by cosmic standards, enormous relative to the planet it orbits. A companion whose presence subtly shapes our seasons, our tides, our axial stability. A companion made, almost certainly, from the wreckage of a world that no longer exists. The universe doesn't build these things gently. It builds them through catastrophe, and then, sometimes rarely, in ways that remain genuinely difficult to explain. What's left turns out to be exactly what was needed. If that story is the kind that keeps you awake in the best possible way, the kind that makes the night sky feel less like scenery and more like a crime scene with beautiful consequences, then subscribe. Stay here. Because the solar system is full of survivors, and we're only beginning to understand the price they paid to be here.